Hello and welcome to the Open Heat Transfer course Conduction. This course is brought to you by RWTH Aachen University and the University of Twente. My name is Wilco Rose, and in this video we will have a first introduction into transient heat conduction. The learning goals of this video are as follows. First of all, we need to categorize different transient problems. This requires an abstraction of the problem and an understanding of the problem. The problem reduction allows, in the next step, to select appropriate solution strategies for the different types of problems. In the first step, we look at a body with a homogeneous temperature. And for that, we rescale the problem, we look at the relevant dimensionless numbers, and we find a mathematical solution for the differential equation. So, let's review Fourier's differential equation and see what changes as soon as we introduce a time-dependent variable. So heat here in this example is brought into the egg, and of course the temperature of the egg increases up to the point when chemical processes are taking place and it becomes hard. So the temperature of the egg material changes in space and in time, and for that we need to add, of course, to our heat conduction equation, with conduction in all three dimensions of space, also a temporal variable, so the change of the temperature in time. How can we now categorize transient heat transfer problems? So first of all, we can look at the temperature of the body itself. On the one side, the temperature, like for instance of this chip here in the center, can be more or less homogeneous. As you see, the temperature here in the infrared image, the color is uniform, so the temperature of the chip here is uniform. On the other side, the temperature can be non-uniform, as seen here for the food case. So on the outer side of the doner, the temperature is high and we have like a burning of the material, but inside the temperature has not increased that much. So first, differentiation, temperature of the body, either homogeneous or non-homogeneous. Then we can also look at the temperature inside the body. Inside means now in the center of the body, or for this type here also in the center of symmetry. Looking at these four different images, we see that the center temperature here, really in the middle, has not really changed, or has maybe changed only very, very little. But on the other side, here if we look at the last image, we see that also the temperature in the center has changed, and so we might need a different approach to calculate the heat transfer in such two different cases. And last but not least, we have the boundary conditions on the surface of the object. So on the one side, if we have a homogeneous temperature, then there are no resistances inside the body. So we need some kind of resistance, which at the end determines also the time of the process. And here we account for a convective resistance on the outside of the body. So that would look like this here now with the change in temperature. So it's not the homogeneous case, but of course we have a resistance on the outside. Then if the temperature has not penetrated fully into the body, we can also have different types of boundary conditions, either a constant temperature. We can also look at the case of convective resistance, and we could also look at a time-dependent temperature on the surface. This is a very special case. There will be a video online, but this video is more to show you how things work and how more complex heat transfer problems can be solved. So we have convective resistance. We can also prescribe, as here in this case, the temperature, or we can have the periodic temperature at the surface. And in the case that the heat has fully penetrated into the body, we will look at a boundary condition with a convective heat transfer resistance. So we have different cases that we would like to go through in the next few videos. And in this video, we will look on the first part here, so where we obtain, because the spatial dependencies are not given, the temperature is homogeneous, a purely time-dependent solution of the problem. Now, that will be for the next lecture, where we look at a one-dimensional approach, and then the third lecture will look on the case where heat has fully penetrated in the object or has penetrated in the center of the object, and this we will do on symmetric bodies, and we will look at a graphical solution for that. But now let's look in this video on the first simplest case. And for that we will have a short review on the Bayer number, what conditions must be met, of course, to have a homogeneous body temperature. And we have seen this already for the fin type problem, that a homogeneous temperature profile inside the body with the high temperature change, or the only temperature change on the outside, will require a small Bayer number. So that means that the heat transfer resistance inside the body, the conductive resistance, is not present or negligible, and on the other side, that the heat transfer resistance here on the surface is a dominating one. If the Bayer number is approximately 1, both resistances are of equal quality and they both affect the body temperature. And for large Bayer numbers, this means that the temperature or heat resistance inside the body is much larger than the resistance on the surface, and as such, we could directly prescribe the environmental temperature on the surface itself. Now, we look at the left case where the Bayer number is small. This here is now an example, and the example looks like this. We have here a sphere, a copper sphere, so a high thermal conductivity. This sphere has an initial temperature T0, which is above the ambient temperature, and as such, this copper sphere will cool down in the course of time. The heat transfer mechanism that we account for the heat transport from the surface of the copper sphere towards the ambience will be convection, that we describe with a convective heat transfer coefficient alpha. So looking at the energy balance now in words at first, so the change of the internal energy, so the change of the temperature inside the body, will be equal to the heat flux that is going over the control volume's surface, in this case the heat flux that leaves the surface. Because in our energy balance we always state entering heat flux is positive and exiting heat flux is negative. Here the control volume is inside the dashed line, so the heat flux that we draw here is negative. And so on the left side, the change of the inner energy is equal to the negative of the convected heat. Now let's fill this with variables. So the inner energy is nothing else than the heat capacity times the volume times the temperature, and the change of the inner energy is just related here in our case to the change of the inner temperature, and this is equal to the convection description or the convection law, so heat transfer coefficient times the surface area of the sphere times the temperature difference between sphere and environment. Now, this differential equation has one major drawback, and that's drawback is that it's an inhomogeneous differential equation where we have this T minus TA. We have already seen how we can solve this problem by defining a dimensionless temperature. We have done that already for the fin case problem, and we do the same here. We define our temperature, the theta star, equal to the temperature T of T minus T0 divided by TA minus T0. And we know if we take the first derivative of that, we will end up with dt divided by TA minus T0. And if we want to replace this part here, we can also use T of T. Just remember that this orange T is always the temperature depending on time, and here it's only explicitly written to make that clear. So the differential, of course, is then what I've already mentioned in words, that we can directly take the derivative of the time of the temperature, which is the only variable which is depending on time. So it's dt, and the prefactor here stays also. Now we substitute these two expressions into our differential equation, and we end up here with this differential equation. We have brought this ta minus t0 on the other side, and we see that if we take ta minus t0 and ta minus t0, this will end up to be minus 1, and t minus t0 divided by ta minus t0 is exactly the definition of theta star. This yields us an equation for the temperature, or here for the dimensionless temperature, where we have on the right side only variables depending on the time, so the time variable, and on the left side we have the temperature. So this is a method of separation of variables. To solve this, we integrate both sides with the respective boundary conditions, or in this case, because it's a time-dependent problem, with the respective initial conditions. So let's do that. We say, okay, what happens at time t0? At time t0 here, the sphere has a temperature of t0. We can plug this in the definition of our dimensionless temperature, and we come to the conclusion that the dimensionless temperature at time t0 is equal to 0. So the integration from time t0 to time t will then be performed, and because here we have this theta star minus 1, the integration yields then to the logarithm. So the solution is that it's a logarithm of theta star minus 1 divided by theta star 0 minus 1, and because the theta star 0 is equal to 0, so there we are left with minus 1 on the bottom, we can change this equation by changing here the sign, so it will be a 1 and a negative theta star, and we have the logarithm of 1 minus theta star. This is equal now here to the right part, and we see if we integrate this, we get a time as in a multiplication here for the t. This becomes the prefactor with the time, and for the boundary initial condition here at time t0, plugging in a 0 in that will remove this term. So we are left with the one term. We can rewrite this equation, the logarithm, by using the exponential or logarithms laws, and then we can rewrite this that the theta star, the dimensionless temperature, is equal to 1 minus the exponent of minus alpha times A divided by rho Cp times the volume times T. So it will be an exponential decay of the temperature starting with the initial temperature. Now, this here is all in dimensional space. I would like to rewrite this equation in dimensionless space, and for that we have to look at the dimensionless numbers that are relevant. So the first one we already had, that's a bio number that describes the ratio between the resistances on the outside and the inner side, and we assume that the bio number is small for our problem. The other relevant dimensionless number is a Fourier number. So it is the thermal diffusivity times the time divided by the length square. But before going into that, I would like to give you more information on the Fourier number. And to derive the Fourier number, we start here with the very simple case of one-dimensional conduction, transient conduction, where we only have one direction. So to make this equation non-dimensionless, we have to introduce variables. So the dimensionless variables t star, t, and x star, and the dimensionless variable times a reference temperature or a reference time will then be the time and the temperature, and the same applies for the spatial coordinate x. So these star variables are the ones that are dimensionless, and the reference values are, of course, the reference quantities. Now, replacing the temperature T by T star times T ref and the other variables as well, we know that those reference values are constant, so we can remove them from the partial derivative. And nicely, we end up here with a prefactor in front of the first term and also a prefactor in front of the conduction term. Because we have these two prefactors, we can combine them in one prefactor, removing all the prefactors here in front of the first derivative, and we end up with a single number that is characterizing our problem. So because here's T star divided by T star, this on the left side is a completely dimensionless number. On the right side we have T star divided by X star and again X star, so this is also dimensionless, which then means that the remaining part also needs to be dimensionless, what we expect. So we have found another dimensionless number that characterizes the problem, and this dimensionless number is called the Fourier number. What does the Fourier number mean? So the Fourier number is a dimensionless time parameter, and it describes the duration of a thermal process in relation to the duration of heat transport. So it just compares how long does it need to heat up the body based on the heat capacity to how much heat is transported towards the body by heat conduction. Now, knowing that we have now the second dimensionless number, namely the Fourier number, we can introduce these two numbers in our problem. So we had this prefactor here, which is a dimensionless, which is a time, because we have to multiply it also with the time. So this factor here has also the units of time, or 1 over time. So look at the area and the volume, both scale with the length, 1 squared, 1 by the power of 3. So we can replace this by L, by the length scale. And we have seen that there was a length scale by 2 and by 3. We can reduce this, so we have a length by 1 and the length by 2. Looks a bit silly, but we can see here that we have two dimensionless numbers here. On the one side the Biot number and on the other side the Fourier number. So the entire problem that we have pointed out, so this block capacity model, will yield to a unifying differential equation, or to a unifying solution, which then describes the heat that is changing from 0 to 1 over time, and the time scale here is the combination of the dimensionless numbers Biot and Fourier. This was the solution of the very, let's say, simple case where we don't have any spatial derivatives. For the next lecture, we will look into the semi-infinite body problem, which means that heat flow penetrates into a body. The question is, where does the temperature change at the beginning of the experiment? So our intuition would say that we have to change only here in the left part if we have a very short look at a very short time, and this temperature on the other side is not affected. On a mathematical way, if we have a solution for that, we will see, of course, that there is everywhere a change, but this change is very small. Now, if we have this problem, we can draw the temperature profile, and as I've mentioned before, the temperature changes severely here in the initial part or in the left part, and on the right side there's nearly no change. So this allows us, because it doesn't matter if we have a wall that is in size as here drawn here, or if it's a larger wall, the solution would be the same, and the boundary condition on the right side becomes irrelevant for the problem, which then is a definition of the semi-infinite body. So this is a body or an object where the temperature change imposed on the one side has not significantly propagated to the other side. And this allows for a special solution, because we can assume a temperature in the infinity which is equal to T0. I would like to go into that in the next lecture, where we look at semi-infinite plates. The last type of problems where the temperature is non-homogeneous but does fully penetrate into the object will then be tackled with the help of a combination of dimensionless numbers and the Heister diagrams. These are solutions or pre-calculated solutions that you can use and that are then applicable if the dimensionless numbers are equal to the one in the experiment. And if this is not possible, of course, other tools can be used, like for instance numerical simulations. If we look here, for instance, at a plate that is heating up a pancake or a food, and we have a complex temperature distribution inside this plate. With that, I'm at the end of my presentation here. A few questions again. So first of all, under what conditions can the temperature within a body be assumed to be homogeneous? This is the case if the bio number is small, which means that the thermal resistance inside the body is much smaller than the thermal resistance on the outside, and this will lead to a nearly homogeneous temperature profile. I'd like to refer you to the topic of fins, where we had the same issue already. Then, which dimensionless numbers can be used for this purpose? There was a purpose for the homogeneous temperature. That's, of course, the bio number. Now, the last question, what does the Fourier number describe? The Fourier number is again a dimensionless number that results from the transient heat conduction equation, and it describes the time required to cool down an object because of its energy content compared then to the heat conduction through the body itself. And with that, I would like to thank you for your attention and have a nice day.